Hello again. So today we will finally be getting to calculus. Yay! So today we'll be talking about this concept called a limit, the limit of a function. This is section 2.2. All right. So for limits, we have this formal definition that looks really long and really scary. But essentially, in terms of the definition of a limit, what I want you to know is this. This is the definition of a limit. So this notation is read as this. The limit as x approaches a of f of x is equal to L. So L is the limit of the function f of x as x approaches some unknown value or known value, some random value point A. Um, so let's see if there's anything here. Yeah, so as x gets closer to a, f of x gets closer to L. So this is kind of the definition that you can write down if you want to be writing down a definition. This is the notation that we're going to use. All right, and we have a couple different ways to find limits, specifically three. So we have graphically, numerically, and algebraically. All right, so to start, graphically is kind of the easiest way because you can just kind of look at it and be able to comprehend exactly what's going on. So the limit, again, is the idea as x approaches some value. What is f of x, where f of x is your y value? So here, we're looking at the limit as x approaches -1. So here's -1. We are looking at the limit as x approaches that value. And what we need to do is we need to decide what this number is. And how to do that is we kind of want to look at what number it approaches. And the only way we can tell what it approaches is if the left-hand side and the right-hand side are actually the same thing. And so we use kind of what's called, or what I call like the pencil method. So what I mean by that is you put your pencil down somewhere to the left of your value and you trace it until you hit the value. All right. And then you go to the other side of the value and you trace it until you hit that x value as well. If your pencil would hit the same exact point, then your limit exists. And the limit, oh, g of x, sorry, not f of x. I always assume that it's just f of x, but it's not. Sometimes we can call things other things. The limit of your function here, g of x, is that point that it touches. So here it is 1, 2, 3. All right. Now you notice there's no point here. An open circle means there's no point. You don't need a point to be a limit. A limit means like if there were to be a point, what would it be? Because you notice there is a point up here, except that point isn't where we would expect it to be. So we don't necessarily care about where that point is right now. That's just some random point that they put on there to throw us off. Now the limit is just where it approaches. All right, now if we're looking to find a limit using a table, we can use this idea. Now, this is kind of big and kind of scary, so let me just kind of give you the rundown. Essentially, what we want to do is we want to choose values really, really close to the x value we're looking at. And we're looking at it from the left and from the right. So we want to look at numbers really, really close. And numbers that are really, really close are usually like 0.0001 away. Typically, I would use maybe these two values and maybe these two values. So this is from the left, and this is from the right. So you don't necessarily need to write anything over here down. This is just kind of a way to show you in a table what it could look like. And this just means plug in these values into your function. It looks a lot scarier than it is. We'll do an example. And this next part, again, looks even scarier. This just says kind of the same thing that I just said. So you're going to take your A values and you could start close and get further and further away. And if those values seem to be approaching the same exact number from the left and from the right, then you have a limit, and the limit is just that number. All right, you don't need to write down really any of that. Just understand the idea of approaching from the left and from the right. Same number, that's the limit. If it's different numbers, there's no limit. All right, so here's an example. So we have this limit as x goes to 0 of the sine of x over x. And we want to see if there's a limit as x goes to 0. So at 0, what's happening there? So what we do is we create a table because I don't know about you, I don't know what that looks like. So we want to create a table of values to figure out exactly what that looks like. So they start off over here and they start off kind of close, but not super close to 0, but they get closer and closer from the left. So let's start with negative 0.1, but then they say, well, we could get closer, negative 0.01. What about negative 0.001? And the more zeros you add, the closer you are to the number, the more valid your answer will be, the more likely you are to have the right answer. So you notice as you get closer and closer to 0 from the left, so again, this is left, you see your numbers are 0.998, 0.999, more nines, more nines. And so essentially, once you get to this point, that's pretty much just 1. So I would say this is approximately 1. All right, now let's check the other side. Let's check from the right. So now instead of negative, because it's from the left, it's going to 0. So negatives would be the left of 0. Positives will be the right of 0. We'll do the same thing, 0.1, 0.01, and this one down here, 0.0001 is honestly the one that I care about the most. So I look at this, I see that they're all kind of the same number, except that they're getting closer and closer to one specific number. That specific number is approximately 1. Because these two numbers are the same exact number, we have an answer. So the limit as x approaches 0 of, again, now I'm writing f of x, but we actually have a function here. Haha. Okay. Of the sine of x over x, we know since the left-hand limit is equal to the right-hand limit, the limit of the function is just 1. All right, and this is the graph of the sine of x over x, and this is just kind of demonstrating that we have the right answer. You notice that there's actually no value here because we know sine of x over x, sine x over x at 0. When you plug that in, we have 0. You can't divide by 0. That's an issue. But if there were to be a point, it would be 1. That's how we indicate it. All right, that's the graph. This is just kind of a general concept. So if we're looking at the limit of x, which we don't typically do, we like the limit of f of x. We want the y value. So the limit of x as x goes to a is just going to be a, and the limit of c for some constant c, we don't care. So we can say like the limit of 5 as x goes to a is just going to be 5. So these two things, honestly, we're not going to use a whole lot, but it is a theorem. All right, we have another example. So we're looking to find the limit as x goes to 0 of the sine of 1 over x. All right, so again, we'll want to look at numbers close to 0 from the left and close to 0 from the right. So we see we have a bunch of numbers, but it goes even further out this time. And that reason is because the numbers are kind of wacky. So you notice when we start close to 0, we're about at a half. And then we're a little bit under that. But then we jump to a negative number. But then we jump to a positive number. And then a negative number, kind of close to 0. But then a positive number, not near 0. And you notice it's kind of fluctuating quite a bit. There's no solid answer that we can get from this that we can say, oh, it's getting really close to this one thing. It's just kind of crazy. And you notice on the other side, when you plug in values going up from 0 closer and closer to it, you have the same exact thing, but negative. So again, crazy numbers. There is no one number that it gets close to like the other one. The other one was getting closer and closer to 1 as the numbers got smaller and smaller. But this, somehow we went from close to 0 to a bigger number or a smaller number. When I see that, that indicates to me that it's not going to stop doing this craziness. And so what we say is that the limit as x approaches 0 of the sine of 1 over x equals, we can kind of denote this a couple different ways. I'll usually say DNE, which stands for does not exist. So if it doesn't approach any solid number, you're just going to want to say that it doesn't exist. And you can check that graphically as well. So here's a graph. As you can see, that's crazy, right? If you look at 0, well, you can't because it's too crazy. And that's kind of the point. You can keep zooming in if you were to like use a graphing calculator. You zoom in, and it's going to look like that the entire time. So you're always going to have this kind of up and down, and there's not going to be a limit at any given point at 0. All right, now we can come to the idea of one-sided limits. This is where we can actually almost define the limit properly. Even though I've given you the definition, I've said that a limit is when the left side and the right side go to the same place. There is a formal definition using one-sided limits that we will get to. So the idea of a one-sided limit is you can look at it coming from the left or from the right, and they're two separate things. And so here, right here, is the definition of a limit from the left. So this is limit from the left. And we notice that it's from the left because we have a superscript minus. This is a superscript. Script, I can't spell. That's why I do math though, right? This is a superscript. So some people will accidentally confuse this with like a minus sign. This isn't a minus, this is just a superscript denoting that we're coming from the left. Sometimes you can have a minus. You could have like -3 to the superscript of minus, saying that we're coming from the left, looking at -3. So just be mindful of that. So this is the limit from the left, which means that if you have some graph and it's like this, and this is 4, coming from the left is looking this way. So you're putting your pencil down on the left and you're kind of tracing up and hitting the point of your x value that you're looking at. Now this here is the definition of the limit from the right. And so again, if you had some kind of a function, I can even give like a slightly better function. If you have this, and then you have this, from the right is kind of taking away the idea that you thought you had of reading a book from left to right, and now we are doing it differently. So if you're looking at this superscript of plus from the right, means put your pencil on the right and draw until you hit whatever your a value is. And say this is like -6, then your answer is -6. All right, I know this is a super confusing idea. So we will do a little bit of practice just to help us wrap our heads around it a little bit. All right, so here we have a piecewise function, and we're asked for the limit as x approaches 2 from the left and the limit as x approaches 2 from the right. Again, that's not a negative, that's just saying from the left. So if we're given some sort of a graph, or if we're given, in this case, a piecewise function, what we can do is we can use that idea from before, saying that from the left is just a teeny tiny bit less than the value we're looking at. And we can plug that value in to whichever function it would apply to. And we'll choose which one it applies to based on the domain that the function is attached to. So if we're looking at 2 from the left, then maybe I want to plug in a number like 1.999. That seems like a valid point, right? So where would 1.999 fall? Well, that is less than 2. So that falls into this first equation. So the limit as x approaches 2 from the left of f of x is x, which we can say, all right, let's use 1.999 plus 1, which is 2.999. And in fact, if I chose 1.9999, this would be 2.9999. And we see as we keep adding 9s to it and we get closer and closer to that value of 2, this value gets closer and closer to 3. And so we'll say this limit is approximately 3, because 2.999, when you round it, is approximately 3. Now, coming from the right, we're looking for a value slightly greater than 2. So typically, I'll just choose a number slightly greater than, and I won't go ahead and use an entire table if I know that the function that I'm looking at is continuous. Now, with like sine of 1 over x, I don't know necessarily what the function looks like, anything about the continuity of it, so you would want to make the full table. But for x squared minus 4, I know it's a continuous function, so I can just go ahead and choose whatever number that I want and assume that the number that I choose, maybe that's slightly closer, is just going to be slightly closer because it is continuous. There's not going to be any crazy jumps going on. So 2 from the right, maybe I'll choose 2.001. We'll stick with like three decimal places. So 2.001, we'll decide where that falls. that is slightly greater than 2, so that goes into, let's call it the second equation. So 2.001 squared minus 4 is approximately 4 point, let's see here, 000. I'm not sure how many zeros. Let's check. 2.001 squared. 4 point, okay. This is 4.004001 minus 4, so that's what 2.001 squared is, which when you subtract that is 0.004001. And in fact, if you chose a number even closer to 2, which say it's like 2.0001, you'd get a smaller number, and you can say this is approximately 0. So therefore, the limit as x approaches 2 from the right of f of x is 0. All right, and this is the graph of the function we were just working with, and it kind of shows exactly what we just found. So we said the limit of the function f of x as x goes to 2 from the left. So coming from the left, hitting 2 was 3. Well, that's 3, so we're right. And then we said the limit as x goes to 2 from the right. So we put our pencil on the right and we go down until we hit 2. Okay, we hit 2 there, that's 0. So we just confirmed our answer. All right, now we can get to the formal definition. So we have this definition of a limit, and it says the limit as x goes to a of f of x. This is the limit if and only if the limit of f of x as x goes to a from the left equals L, and the limit as x goes to a from the right of f of x is L. So if the limit from the left and the right are the same thing, then the limit exists and the limit is that number. If, however, the limit as x goes to a from the left is some number, say 3, and the limit as x goes to a from the right is some number, say 5, the limit wouldn't exist at all. Now, your left and right hand limits would exist, but the limit at that point would not exist. So this is the formal definition of a limit. Oops, sorry. We also have infinite limits that we could see. So given some type of function, we have two different ways that we can kind of look at this. I don't expect you to memorize what this would look like, but it's kind of cool to look at. So if you have 1 over x minus a to the n, where a is just some random number and n is an odd positive integer. So say a is 0, you have 1 over x cubed. Then you have a function that looks like this. So it goes down on the left and up on the right. And so the limit as x goes to a from the left will be negative infinity and from the right will be positive infinity. So we may have limits that are some type of infinity. And if it's an even positive integer, they both go to positive infinity. Now, again, these are not something that I expect you to memorize. It's just something interesting to kind of look at. All right, so let's try to evaluate these limits now. So we have the limit of 1 over x if x approaches 0 from the left. So I'm not going to use those rules that we just said. I'm going to go ahead and do it the way that you would be expected to do it, maybe on homework or anything like that. So what I'll do is I will use a table. So the limit as x goes to 0 from the left and from the right, and then we'll see if those two things are the same thing, and we would have an actual limit. So let's make a table. We'll say, oh, that's a highlighter. I don't know why I'm doing that so much. Sorry, guys. We'll say x, f of x, and then I'll make another one, and I'll say x and f of x. And we'll do this one as the left and this one as the right. And since it's 0, 0 minus 0.01 is negative 0.01. Let's go even closer. Let's go 0.001, negative 0.0001, and let's go negative 0.12340 zeros 1. Because the closer we get to it, the smaller the number, the more accurate we're going to be. Or the more likely we are to see what's actually happening. So I'm not going to do 0.1 because honestly, that's just kind of, it's not going to give you a whole lot. All right, and then I'm going to do the same exact numbers on the right-hand side, except I'm going to do those with positives. So 0.001, 0.0001, and then 0 with 4 zeros, 1. All right, and now if you were to divide 1 by negative 0.000 or 0.001, what we get is negative 1,000. 1 divided by negative 0.0001 is negative 10,000. And 1 divided by this guy here is negative 100,000. And what you notice is these are increasing. I want to use the word exponentially, but it's not actually exponential, but they're increasing very, very, very quickly. So if you did another decimal place here, it would be negative 1,000,000, and so on. And so the limit here, as x approaches 0 from the left of 1 over x, is negative infinity. Because as you get closer and closer, that number is going to get like infinitely bigger in the negative sense. Over here, same idea. 1 divided by 0.001 is positive 1,000. Here you'll get positive 10,000, and here you'll get positive 100,000, and so on. So what we see here is that the limit as x approaches 0 from the right of 1 over x is going to be a positive infinity. And so here we have negative infinity, here we have positive infinity, but the formal definition of a limit is that the left-hand limit and the right-hand limit have to be the same. If they are, then that's the limit. Negative infinity is not positive infinity. Therefore, the limit does not exist. All right, this was kind of what we were talking about before. It's just kind of interesting to note, but again, you'd kind of be expected to show work for everything, so you don't need to like remember this theorem or anything like that. You don't need to necessarily write it down even, because again, it's something that you'd be expected to show the work for if you ever had to show the work for it. All right. Now we have this idea of a vertical asymptote. So some of you may be familiar with this from pre-calculus. So we have a calculus definition of a vertical asymptote and a pre-calculus definition of a vertical asymptote. So the calculus definition is that if you're looking at a limit from the left or from the right, or just the limit in general, and it approaches some infinity, then it's a vertical asymptote. But I wouldn't write that down if I were you. Essentially, all I want you to remember is the definition from pre-calculus. So from pre-calculus, we know that a vertical asymptote occurs when you have a 0 in your denominator. So if you have, say, 1 over x minus 3 as a function, and you want to see what values the denominator can't be equal to, you would say x minus 3 can't be 0. We did that just a couple lectures ago. So you would say that x can't be 3. Well, what this actually tells you is that x equals 3 is a vertical asymptote. And a vertical asymptote is just a vertical line that a function can never cross. And so this function would look something like at 3, this is x equals 3. It would go like something like this. So the function is never going to cross that. So this is the definition that I want you to remember, not necessarily the calculus definition. I also don't know if I'll actually ask you to find a vertical asymptote. Let's do an example though. So again, this is 1 over x plus 3. All of these limits will be the same exact idea. So to find the limit, of these, if you were asked to do them, you could use a table method. This just says find the vertical asymptotes. So all of these have the same vertical asymptote, and that will be at x equals negative 3, because we know that x plus 3 cannot be 0, which means that x cannot be 3, negative 3, which means that we have a vertical line at negative 3 that we just can't cross. So while you could theoretically find the limit, here it's asking you to find the vertical asymptote, and it does also say evaluate the limit. If you want to do that, you can go ahead and try plugging that into your table. The trick is here you have an even number. You know that means that everything down here will be even. So if you have x equals 3 here, You have any negative number to an even, that'll be even. Any positive number to an even will be even. Your function will look something like this. And so all of your limits here will be equal to positive infinity. You can go ahead and check that if you want using your table method. All right, this is the last question of the day. It looks kind of crazy, but this is often a question that you'll get in calculus. So you will get this crazy looking question where you are expected to go ahead and look at this function and figure out every single thing. So what I want to note is if you see f of a point, so f of 4, f of -2, that is the point. That is the solid closed circle point. That means that you have to have a point defined there. If there's an open circle, that doesn't count. If there's a closed circle, that's the point. If there's no closed circle, there's no answer. All right, so let's go ahead and try this. Let me move my little icon. All right, so A says we're looking at the limit as x approaches -4 from the left of f of x. B is the limit as x approaches -4 from the right of f of x. And C is the limit as it'll just be the general limit that we're looking at here, which is as x approaches -4 of f of x. So I know there's a lot more. Let's just do these first because they're all related. So here's -4. All right, from the left means you put your pencil to the left and you go up and it hits right here. That is at 0. From the right means you put your pencil somewhere to the right of that value and you draw until you hit that value. It hits right there. That's 0. Because the left-hand limit and the right-hand limit are the same thing, they are both 0. That means the limit at that point is 0. All right, not too bad. Oh, I see these are just labeled A, B, C, D. I guess I can change it. So A is just this whole thing. Seems silly to me, but whatever. I didn't make the textbook. Now it's asking for f at -4. Well, this, I can erase the little drawings that I just did, is just a line. So while there's not like distinctly a closed circle obvious point, there's just a function going through it. Because of that, there is a closed circle point, and so therefore the closed circle point here is just 0. Now B is looking at -2. So we're saying the limit as x approaches -2 from the left of f of x, the limit as x approaches -2 from the right of f of x. We want to see if that limit exists. And then we want to see if the point at -2 exists as well. So we'll go -2 now. So again, we'll put our pencil on the left-hand side, draw up. Once we hit -2, we stop. That is at 3. So this is 3. All right, now for the right, we go a little bit to the right of this value. We put our pencil down, we draw, we hit -2, and we stop. That's also a 3. Perfect. Because the left-hand limit and the right-hand limit are the same, that means the limit in general is, in fact, 3. But now they're asking for the point. What is f at -2? Well, we see there's an open circle here, and there's no closed circles anywhere. Therefore, there's no point. This does not exist. All righty. What about C? This is looking at 1. So the limit as x approaches 1 from the left of f of x, the limit as x approaches 1 from the right of f of x. See if the limit at 1 exists, and then see if the point at 1 exists. All right, so again, looking at the limit from the left, put your pencil down, go up until you hit the x equals 1, and we see this is at 6. The limit from the right goes slightly to the right of 1, draw until you hit that point, that is at 3. Now the limit has to be only when the left-hand limit and the right-hand limit are the same. Well, 6 doesn't equal 3. Therefore, the limit at that point does not exist. Now the point, we have to ask ourselves, is there a closed circle point somewhere? And the answer is yes. The closed circle point at 1 is in fact right here, which is at 6. All right, last one. Now we're looking at 3. So the limit as x approaches 3 from the left, the limit as x approaches 3 from the right, the limit as x approaches 3 in general, and then is there a point there? All right, so first from the left, let me get rid of the drawings that I have here. From the left, here's 3, we draw, but what we notice is that we never actually hit a point. We would draw and we could draw forever. So that indicates that we're going to sum infinity, and we'll just decide if it's positive or negative. Since we're going down, this is going to negative infinity. From the right, we again go slightly to the right of 3, which is about here, and we draw. But again, we see that we never actually have an end because this graph goes on forever. Well, it's going down forever, which means that we are going to negative infinity. Okay, well, that means that the limit at that point does in fact exist. Even though infinity isn't a number, infinity is a limit. And so we can say the limit at 3 is negative infinity. Now, f of 3, that says, is there a point there? Well, we know it's never going to touch 3. This is what's called a vertical asymptote here. So you can theoretically draw some dotted line here, and you are never, ever, ever going to cross that dotted line. So this point here does not exist. All right, that's all I got for you today. I hope everyone has a great rest of their day.